Dear students, I am Angad Naik, Assistant Professor, Department of Mechanical Engineering, SGBIT, Belagavi. I welcome you all to session 4 of Module 5 on spur gears and gear trains. Today, we'll try to discuss on conjugate action in this session. Gears must be designed such that the ratio of speed of driven and driver gear is always constant. When the tooth profile of two meshing gears produce a constant angular velocity during meshing, they are said to be executing conjugate action. This we'll try to analyze with the help of animation. In the animation, you can see there is one curved surface pushes against another. The point of contact occurs where the two surfaces are tangent to each other, and the forces will be directed along the common normal, which is also called the line of action or the pressure line. The line of action will intersect the line of center set point P, which also defines the point of tangency of the pitch circles of the two meeting gears, and it is called as pitch point. Any two curves or profiles engaging each other and satisfying the law of gearing are conjugate curves, and relative motion or relative rotation speed of the gears will be constant. We'll try to illustrate the conjugate action with the example or with the illustration. Wrap string around base circle. The red circle is base circle. To this base circle, the string is wrapped. To one end of the string, pen is attached. The whole setup is placed on a paper. As the string is unwinded, the pen makes mark on the sheet. The resulting line is an involute. Involute starts at base circle. We'll see the animation. The blue one is the base circle. The black dot on the blue circle is the starting point where the pen is placed. As the process of unwinding the string occurs, the path traveled by the pen on the paper is realized in the animation. With this note, we'll try to move to the next topic, which is path of contact. We'll try to see the animation first and then go to the description. In this animation, there is a point, red dot. It is traveling a particular path. The path traced by the point of contact of two teeth from the beginning to the end of engagement, that whole path is called as path of contact. Now let's see the description. Path of contact is the path traced by the point of contact of two teeth from beginning to the end of engagement. We'll try to draw a figure and derive an equation for the same. In the figure you find there is wheel and pinion. Wheel has center O1, pinion has center O2. To draw this, we'll first take the distance between O1 and O2 as 9 centimeter. The midpoint of 9 centimeter is 4.5. So with the help of compass, mark 4.5 centimeter and place it on O1 and radius equal to 4.5 centimeter. Draw a curve. Name that curve as pitch circle. Same process is repeated for pinion with center as O2, radius equal to 4.5 centimeter. Draw a curve. Name it as pitch circle of pinion. The point where the two circles meet is called as pitch point. Then take 3 centimeter in the compass and draw one more curve with center as O1 and O2. Name it as base circle of wheel and base circle of pinion. To draw the addendum circle, take O1 as the center and radius slightly higher than pitch circle, but this distance should not touch the base circle of the pinion. So in such a way, draw addendum circle of wheel. Similarly, draw the addendum circle for pinion without touching the base circle of wheel with center as O2 and radius slightly more than the pitch circle. Now we'll consider that the pinion is driving wheel as shown in figure. There are few more elements drawn. You can see the profile of the teeth have been drawn. MN is the common normal at the point of contact and common tangent to the base circles. The point where there is contact between the pitch circle is labeled as P. Point P is very important to the velocity ratio and it is called as pitch point. Now the other elements are labeled. MN is the common normal. On this common normal there is a point P which is pitch point. As we saw in the animation, the point of engagement begins at K and ends at L. So when the pinion rotates in clockwise direction, the contact between a pair of involute teeth begins at K and ends at L. Some other constructions are also added. From O2, a line is drawn to K. Similarly, from O1 to L, a line is drawn. The angle framed by PO2N is marked as phi. Similarly, O1MP is marked as phi. K is the point where there is intersection of the addendum circle of wheel and the common tangent. Point L is the intersection of addendum circle of pinion and common tangent. We'll now modify the figure. The length of path of contact is the length of common normal cut off by the addendum circle of the wheel and the pinion. Thus, the length of path of contact is the length KL, which is part of KP and PL. Contact length Kp is called as path of approach and contact length PL is called as path of recess. If you combine path of approach and path of recess, then we get path of contact. Now we'll try to label the radius of pinion and wheel. RA is the radius of addendum circle of pinion. Capital RA is the radius of addendum circle of wheel. Similarly, radius of pitch circle of pinion is labeled as small r and radius of pitch circle of wheel is named as capital R. Radius of the base circle of the pinion is O1m. If I consider the triangle O1MP, the angle subtended at the center is phi. Cos of phi is adjacent side by hypotenuse. Hypotenuse is O1P and adjacent is O1M. So cos phi is equal to O1M divided by O1P. Therefore, O1M is equal to O1P into cos phi. The same is written in the equation. By geometry, one can find that O1P is written as small r. Similarly, radius of the base circle of wheel is O2n. In the triangle O2NP, the angle subtended at the center is phi. Cos of phi is adjacent by hypotenuse. Adjacent side is O2n, hypotenuse is O2p. So cos phi is equal to O2n divided by O2p. Therefore, O2n is equal to O2p into cos phi. The same is written in the equation. If you see the geometry of the figure, O2p is named as capital R, which is the radius of pitch circle. So it is rewritten as capital R into cos phi. From right angle triangle O2KN, by applying Pythagoras theorem, we can write Kn is equal to O2k square minus O2n square. O2k is nothing but Ra square. O2n is R cos phi. So it is written as square root of Ra square minus R square cos square phi. Pn is equal to O2p sin phi. O2p is capital R, so it is written as R sin phi. Path of approach is defined as Kp in our earlier slides. So Kp is equal to Kn minus Pn by geometry. By substituting the values of Kn and Pn, that if we have got from the triangle O2Kn, if we substitute in path of approach equation, we get square root of Ra square minus R square cos square phi minus R sin phi. Similarly, from right angle triangle O1M L, ML is equal to O1 L square minus O1 M square by Pythagoras theorem. O1 L is nothing but radius of addendum circle of pinion. So O1 L square can be written as Ra square. O1 M can be written as R square R cos phi. So O1 M whole square is written as R square cos square phi. So ML is O1 P sin phi. O1 P is nothing but the radius R, so it becomes R sin phi. So path of recess is PL. PL can be written as ML minus MP by simple geometry. Substituting the values of ML and MP in the path of recess equation, we get square root of Ra square minus R square cos square phi minus R sin phi. Hence, the total equation of path of contact, which is KL, can be written as Kp plus PL, adding the equation that we got from path of approach and path of recess together is square root of Ra square minus R square cos square phi plus square root of Ra square minus R square cos square phi minus R plus small r into sin phi. This is the final equation of path of contact. This ends the session. Thank you for your patience hearing.